Welcome to this video where we dive into the fascinating world of the Zero Modular System, or ZMS for short. ZMS is a unique way of handling modular arithmetic where the modulus isn't fixed and can even be zero. This system brings new rules and notations that redefine how we think about division and remainders. Let's get started. What is ZMS? Zero Modular System, or ZMS, is a new take on modular arithmetic. Normally in modular math, we use a fixed number called the modulus. But in ZMS, the modulus isn't fixed, and it can even be zero. Here's how it works. First, if you take any number and divide it by zero, the result is the number itself. For example, 1 over 0 equals 1, and 1,000 over 0 equals 1,000. This is because in ZMS, all integers are included when using mod 0. Second, if one number is greater than another, then dividing them gives you the remainder. For example, 8 over 3 equals 2, because 8 leaves a remainder of 2 when divided by 3. In ZMS, we care more about the remainder than the quotient. Introducing new notation, ZMS comes with its own special notation to describe these modular relationships. If you divide a over b and get a remainder, we write it as a over b equals r mod b. For example, 8 over 3 equals 2 mod 3. This means 8 leaves a remainder of 2 when divided by 3. If you want to compare two divisions and see if their remainders are the same, we use double mod. We say a over c equals b over c double mod c. This means both divisions leave the same remainder when divided by c. In other words, a and b are both equal to that remainder when using mod c. We use the pipe symbol to represent mod, but we'll call it mod for simplicity. Examples to understand ZMS. Let's see some examples to understand how ZMS works. 8 over 3 equals 2 mod 3 because 8 leaves a remainder of 2 when divided by 3. 10 over 4 equals 2 mod 4 because 10 leaves a remainder of 2 when divided by 4. 0 over 0 equals 0 mod ZMS. All numbers over 0 equal themselves. 1 over 0 equals 1 mod 0. And 1,000 over 0 equals 1,000 mod 0. Finding a pattern. Next, we looked at the pattern of powers of 2 using binomial expansion. We expanded 1 plus 1 to the power of 2, then 3, and so on, up to 5. Here's what we got. 1 plus 1 squared equals 1 plus 2 plus 1, which is the same as 2 squared. 1 plus 1 cubed equals 1 plus 3 plus 3 plus 1, which is the same as 2 cubed. 1 plus 1 to the power of 4 equals 1 plus 4 plus 6 plus 4 plus 1, which is the same as 2 to the power of 4. 1 plus 1 to the power of 5 equals 1 plus 5 plus 10 plus 10 plus 5 plus 1, which is the same as 2 to the power of 5. We notice that every expansion starts and ends with 1. To get rid of the ones at the beginning and end, we subtracted 2 from each expansion. 1 plus 1 squared minus 2 equals 2. 1 plus 1 cubed minus 2 equals 3 plus 3. 1 plus 1 to the power of 4 minus 2 equals 4 plus 6 plus 4. 1 plus 1 to the power of 5 minus 2 equals 5 plus 10 plus 10 plus 5. This gave us a general pattern. 2 to the power of x minus 2 equals the sum of the remaining terms. General formula. We then turn this pattern into a general formula. 2 to the power of x over x equals 2 over x, double mod x. This means the remainders of both sides are the same when over x. Since x plus 1 over x equals 1, mod x, we multiplied both sides by x plus 1. 2 to the power of x over x times x plus 1 equals 2 over x times x plus 1 double mod x. This simplifies to 2 to the power of x equals 2 double mod x. Since 2 over x equals 2, mod x for x greater than 2, we can simplify this to 2 to the power of x equals 2 mod x. Testing for primes using ZMS. In ZMS, we can use this formula to test for prime numbers. 2 to the power of x equals 2 mod x. If this holds true, then x is a prime number. Let's see some examples. When x is 3, 2 to the power of 3 equals 8. 8 over 3 equals 2 mod 3. Since this is true, 3 is a prime number. When x is 4, 2 to the power of 4 equals 16. 16 over 4 equals 0 mod 4. Since this is not true, 4 is not prime. When x is 5, 2 to the power of 5 equals 32. 32 over 5 equals 2 mod 5. Since this is true, 5 is a prime number. When x is 6, 2 to the power of 6 equals 64. 64 over 6 equals 4 mod 6. Since this is not true, 6 is not prime. When x is 7, 2 to the power of 7 equals 128. 128 over 7 equals 2 mod 7. Since this is true, 7 is a prime number. Application to Mersenne primes. We can also use ZMS to check for Mersenne primes. A Mersenne prime is a prime number that is 1 less than a power of 2. We use the same method, but replace x with m sub n, which is 2 to the power of n minus 1. If 2 to the power of m sub n equals 2 mod m sub n, then m sub n is a Mersenne prime. In this video, we explored the zero modular system and its unique way of handling division and remainders. We learned new notations and how to use ZMS to test for prime numbers, including Mersenne primes. If you found this video helpful, don't forget to like, comment, and subscribe for more math explorations. Thanks for watching, and see you next time.